This is part 2 of the gas law discussion, continuing with special uses of the ideal gas law. We were talking about gas density and molar mass, and how with a little creative substitution in algebra, we could come to new equations that deal with them specifically. For example, density is equal to pressure times molar mass divided by RT, or rearranging molar mass is equal to density times RT over P. How we can apply these in problems can be seen below. For example, if we want to determine the density of xenon gas at 75 degrees Celsius in a sealed container with a pressure at 2 atmospheres, we could do the following. We can realize that xenon gas is a pure gas, and we can find its mass on the periodic table. We can convert 75 degrees Celsius to kelvins and work with the pressure in atmospheres in the ideal gas law using D equals PM over RT. Substituting again, pressure 2 atmospheres, molar mass of xenon 131.3 grams per mole, R value in atmospheres, and 348 Kelvin, to see that the density of xenon gas is about 9.18 grams per liter. This is pretty high for a gas because xenon's a pretty heavy gas. Most gases don't approach this mass. We could also look, if we know the density of a particular substance, we can use that to find its molar mass. In fact, this is a very common analytical technique for determining the molar mass of unknown gases. So we're going to work under the same conditions and measure the density of a gas to be 2.65 grams per liter. Applying the rearranged form of this equation, we can say that the density times RT over P is equal to molar mass. So my 2.65 grams per liter times the same RT and pressure would generate a molar mass of 37.9 grams per mole. We can make a comparison here and see that as xenon was about 130 grams per mole, this gas is only about 40 grams per mole. This should make sense as the molar, or the density, of xenon is a little under 4 times as high as the density of this unknown gas. So the molar masses should reflect that as well, and they do. The next law we need to discuss is Dalton's law of partial pressure. Essentially, this goes back to our kinetic molecular theory discussion that says that all ideal gases behave the same, and we're going to assume that all gases are ideal unless we're told otherwise. So because of this, the only thing that's going to change is the amount of times they collide with the wall in a container. And so that is going to be directly proportional to the number of those molecules in the container. So if I have a mixture of several gases, then I should be able to treat them all the same. If I happen to know how much of each one is there, or happen to know the pressure of each one, then I can sort them out, because those are the only two things that matter. So Dalton's law looks like this. It says the total pressure is equal to the sum of the individual pressures of the components up to the total number of components. Or we can look at PV equals nRT and solve it for P, so that we have nRT over V, and we can realize the only two things changing are the pressure and the moles. So the pressure of an individual component is equal to nRT over V. One other way we can look at this, if we know the total pressure or total moles, is to know that the pressure of the individual component will be its fraction, its amount in N over the total amount in T, times the total pressure. So for example, if I have two gases making 100 kilopascals of pressure, one of them is 45%, the other is 65%, then each should make that fraction of the total pressure. So the 45% gas would make 45 kilopascals, and the 55% gas would make the 55 kilopascals. So in working with a problem of this type, we can take a mixture of known amounts of gases at a given temperature and in a given container with a certain volume, and determine what the total pressure inside that container should be. First thing we need to do, since we have masses of two different gases, nitrogen and hydrogen, is to determine the amount of each gas in moles. So 2 grams of hydrogen, knowing that there are 2 grams of hydrogen in every mole of the substance, gives me about 0.990 moles of hydrogen. Applying similar logic to nitrogen, only with a molar mass of 28.02 for nitrogen, gives me 0.26 moles of nitrogen. Then I need to find the combined pressure. So essentially I need to find the combined number of moles. Since the gases will behave similarly in the system, I can take the moles of hydrogen, the moles of nitrogen, add them together. That would be N total. And so the total pressure in the system would be N total RT over V. Subbing in from above, we're using kilopascals in this case, just simply because I feel like using kilopascals. And we're using temperature at 273 that they gave me, and we're in a 10-liter flask. We can solve this and see that the total pressure in the system is about 289 kilopascals. The next idea has to do with a lab procedure of collecting gas over water. This is very common, but unfortunately when you collect a gas over water, gas being also volatile to some extent, will enter into the system as well. So this is like relative humidity, things that you feel outside. We have to account for this in the lab as well. So anytime I do this, we're going to include water into that Dalton's law equation. Even if I think I'm just collecting, say, oxygen or nitrogen or something, there's going to be water vapor as well. So here is a look at how to handle that. We have a question asking us about a sample of potassium chlorate that decomposes into oxygen and other things. The volume of that gas is collected in a 0.250 liter container at 26 degrees Celsius, and the total pressure is measured as 765 torr. Just a reminder, torr is just another pressure unit. 1 atmosphere is equal to 760 torr, and so at this point we're just barely over 1 atmosphere of pressure. They want to know how many moles of O2 were collected and then what mass of KClO3 it took to make that. So we have a gas equation question, and then we have some stoichiometry behind that. So the first thing we're going to need is a balanced chemical equation. When chlorates decompose, they make chlorides and oxygen, as told to you earlier in the year. So if we balance the system, we see 2 chlorates making 2 potassium chlorides and 3 oxygens. Next, we need to determine the pressure of oxygen gas all by itself. And so we take the total pressure of 765 torr that they gave us, and then we go to a table. In this case, I just went to the internet and looked up the water vapor pressure system for water at 26 degrees Celsius, which is where we're working, and was told it was 25.2 torr. This is well-known information. It's encountered in the lab all the time, so you can look these up in tables in your textbook, on the web. Any reputable place will work. And so if I make the adjustment, I can see that I have about 740 torr coming strictly from oxygen, or about 0.974 atmospheres. Next, we need to determine the moles of oxygen. This is just an application of the ideal gas law where we're focusing solely on oxygen, so the moles of oxygen will be its pressure times the volume of the container over RT. And since we are operating just with oxygen, we end up with 9.92 times 10 to the negative 3 moles, or a pretty small amount of oxygen. Last, we'll do stoichiometry between oxygen and potassium chlorate to determine that mass. The moles of oxygen we found, 9.92 times 10 to the minus 3. There is a 2 to 3 ratio between potassium chlorate and oxygen, and potassium chlorate has a mass of 122.5 grams per mole. So we see that approximately 0.8 grams of potassium chloride or chlorate could produce the oxygen seen in the reaction. Just to summarize for you the parts of the kinetic molecular theory, we've used these in discussion and explanation of all our previous gas laws, but here we just want to sum them up. So the first idea that we operate under is that gases are composed of large numbers of particles that are in constant random motion. The volume of those particles is negligible compared to the total volume that they occupy. The attractive and repulsive forces between them are negligible. We can transfer energy between those molecules or atoms during collisions only, but no energy leaves the system. This means the average kinetic energy of the molecules is constant over time, so that all collisions are perfectly elastic. If you don't know what this means, think billiard balls. When you hit 2 pool balls one at another, they may go in different directions, they may go with different speeds, but essentially the net energy that you sent in is what comes out. At least in that case, there's some loss to friction, but it's a good picture. And then last but not least, the average kinetic energy of those particles is proportional to their absolute temperature. This means their Kelvin temperature, not their Celsius temperature, not their Fahrenheit temperature, their Kelvin temperature. And at any given temperature, the particles of all gases are going to have the same kinetic energy. Now be aware or remember that this is a theory. This does not represent 100% fact. It's an attempt at explaining what we actually observe happening with gases, so there will be problems with it, but it does a pretty good job at showing general behavior of gases. Some other things that we need to be aware of: How do we get kinetic energy and mu RMS? Mu RMS is root mean speed. So essentially this is like when you're working on a regression line, you would encounter something with a root mean. But essentially this is the average of the squares of their velocities. And because kinetic energy is equal to 1/2 mass times velocity squared and also equal to 3/2 RT, we can work these down through a derivation that I can show you in class if you're interested. But essentially we work this down to the fact that the root mean speed of any gas molecule in a system is equal to 3 times R times the temperature they're moving at divided by the molar mass to the 1/2 power. And so essentially what you see here is that their speed really depends on their temperature, which is going to give them their energy, and their mass, which is going to limit how fast they can move with that energy. In order to work these out, if we're working with actually within this equation, that mass must be in kilograms. This is due to the fact that R contains joules, which has kilograms in it. It's just an artifact of the units, so you must put your masses in kilograms. So if you look up hydrogen, and it's 2.02 grams. Really, that's 2.02 times 10 to the minus 3 kilograms. Be aware of that. Also be aware that mu does represent an average speed, but it is not the average velocity. It's pretty close, but mu RMS is usually just a hair above whatever the average regular speed is. We also want to discuss how this works with mu RMS, effusion and diffusion. They're both going to rely very heavily on the random motion of particles, and they're going to rely also on the fact that kinetic energy is the same for every molecule in a system. The only thing that's going to set that is the temperature. Now, this does not mean that every molecule in the system is traveling with the same speed at the same time. Some are heavier, some are lighter. There's also distributions, but over time as they bump into each other, if we were to average their kinetic energy over a long period of time, we would see that they all come to the same value. And so this should make sense then that the root mean square velocity for heavy molecules is going to be a little bit less than for lighter molecules. Heavy things are able to take that energy and move, but they move slower than the light ones. Effusion is set up like this. It says effusion rate 2 over effusion rate 1 is equal to the square root of the molar mass of the first one over the molar mass of the second one. Something to note here, it is inverted. So these rates, the faster one will have to be lighter. So that has to be reflected in the gases. So it's an inverse relationship. In fact, it's an inverse square relationship. And in case you're interested, effusion deals with the escape of gas through small holes. So this would be like helium escaping from balloons in your room, or if you have tires with tiny pinprick holes in them, this is how air bleeds out of them over time. The lighter gases, as you can see, will escape faster because they're moving faster. They have a higher chance of hitting the walls, finding the hole, and getting out. Diffusion is similar but different. It has to do with random walk also, but it's talking about how far things spread out over time. And if things are spreading out over time, essentially they're bumping into other particles and getting bounced in every which way, and that's how they spread out. And so if we were to just time how far particles travel on average in a given amount of time, that's also going to be inversely related to their molar mass. The ones that are traveling faster can cover a farther distance in the same amount of time. So this is going to be in our discussion of gases, it's going to mean spreading out in space. The last little blurb that I want to throw in here is the van der Waals equation. Several of you have asked in class what happens to these gases when these gases don't behave like ideal gases. They're not ideal. There is no such thing. I'm aware of this. Like I said a minute ago, I gave you the warning about this being a theory. Well, this is one of the ways that we can make adjustments. This is the van der Waals equation. Notice it kind of looks like PV equals nRT, or P equals nRT over V, but there are some extra terms. The first of those extra terms is the V minus NB. This is going to adjust for the fact that atoms do have volume. We said we were assuming they don't have any, but we know better. The next, N squared A over V squared, is going to adjust for the fact that they do attract each other. Even if they are something like helium, where those attractions are very small, there's still induced dipole and dispersion forces going on. So this is not absolutely true either. The problem with this equation and why we don't use it very often is because all of these constants are going to be this B and this A. They're going to be special for each gas, and so that's an awful lot of things to have to figure out and try to sum up when the ideal gas law usually predicts answers within plus or minus 5% under normal conditions, which is where the world operates, and most people are okay with that. The greatest deviations that we're going to see from this behavior, however, are going to be when